Now I'd like to talk about a common collector amplifier. So if you recall, this is what a common collector amplifier looks like. This time there's no resistor on the collector side, and the signal is taken from the emitter. This is often also known as an emitter follower, A, because we're taking the signal from the emitter, but also because this follows the input voltage, as we will see. Now, if you're trying to find the AC equivalent, the first thing to do is all capacitors become shorts. So that's what that looks like. And VCC plus is actually going to become AC ground. That being the case, we can redraw our diagram just as we did before with R1 and R2 in parallel to ground, where I remind you this is R1 and this is R2. But this time, our output is taken from above RE, but we have the transistor resistance RE prime in between. So this is where our output is taken. Now, if we want to calculate the voltage gain is going to be V out over V in. Well, what is V out? V out is the voltage across RE, and V in, of course, is the voltage across here, which is actually the voltage across these two resistors. So the output resistance this is just a voltage divider with a really tiny resistor and a really big resistor, which is to say that most of the voltage drop is across the big resistor. If I were to write this out, V out is IC times RE, and V in is IC times RE prime plus IC times capital RE. And if I were to take the ratio of these two, this is what I get. The ICs cancel out. And since RE is small compared to RE, capital RE, I get approximately 1. And so the voltage gain of a common collector amplifier is approximately 1. Again, this is why it's called an emitter follower. It follows the input, and you have unity gain. Okay, now the voltage gain is not particularly anything to write home about, but the current gain is equal to beta plus 1, where beta plus 1 is the factor of how much current is being driven into the collector, through the emitter by the transistor. And so you get a very, very large current amplification. Now this, of course, explains the advantage of a common collector amplifier. You might wonder, if the common collector amplifier gives you a voltage gain of 1, what's the point? Well, the point is you can optimize it so that the input impedance is very large, and not only that, but whatever this voltage supply is doing doesn't make it across to the other side. The other side of the transistor reproduces the voltage on this side, but you can have a very, very weak power supply generating your signal, something that cannot provide a lot of current. But on the other side, you can reproduce that voltage with a lot of current behind you. So very low power device on the input, you can reproduce the same voltage with a much larger power on the output. And that's the key aspect of this. So our input impedance, just as before, is R1 in parallel with R2 in parallel with Z base, where Z base this time is beta plus 1 RE plus capital RE. And Z out is going to be the resistor, the emitter resistor in parallel to RE prime, which is a small value, plus the effective parallel resistance of R1, R2. And because we're crossing the transistor, it's divided by that factor of beta 1, which makes it very small. And that means that Z out in general is a very small value. And so again, you can especially optimize Z in to have a fairly large input impedance and a very low output impedance, which means, again, you can have a power supply that provides 5 volts on the input, but cannot provide a lot of current to maintain that 5 volts. But since it's a very high input impedance, you don't need a lot of current to maintain that 5 volts. But on the other side, you have this current source that can maintain 5 volts with a lot of current, with a huge current gain, a low output impedance. One of the ways I like to kind of think about it conceptually is that these sorts of circuits that have high input impedance, low output impedance, is like if I were to design a machine to lift something that replicated what I was doing with my body, but able to do it with more power. Like imagine I had a device where if I lifted an empty box, then a robot with really powerful hydraulics could lift a filled box the same height that I lift the empty box. So I don't have to do a whole lot of work, but on the other side of the system, it's reproducing my physical motions, but with the strength to lift, a car or something. So that's kind of how I think about it in terms of the circuit, that you have sort of a wimpy power supply on one side and you reproduce the voltage on another. Similar techniques are often used with operational amplifiers, which, as you hopefully know at this point, have a very high input impedance, almost infinity, and a very low output impedance. And that's all there is. Well, not all there is, but that's all that I'm going to talk about for common collector amplifiers.